Here's what's breaking the laws of physics right now. 3I/ATLAS just lost 63% of its brightness while racing 10 million kilometers closer to Earth. This defies everything we know. Objects get brighter as they approach, not dimmer. It's basic physics. Yet this interstellar visitor is doing the impossible. Scientists have no explanation. The object's magnitude dropped from 10.1 to 10.6 in days, precisely when it should be blazing brighter in our sky. Is its surface fundamentally changing? Are internal processes we've never witnessed at work? We have less than 3 weeks before the observation window closes forever, and what happens next could rewrite astronomy textbooks. Let's dive right in. The numbers are staring us in the face, and they don't add up. Between late November and early December, 3I/ATLAS dropped from magnitude 10.1 to 10.6. That might sound like technical jargon, but here's what it actually means. This object lost 63% of its brightness while racing 10 million kilometers closer to Earth. Think about what that means for a second. Everything we know about how light works says this shouldn't happen. When something moves toward you, it gets brighter. That's not theory, that's basic observation anyone can verify by watching car headlights on a dark road. Yet 3I/ATLAS is breaking this fundamental rule right in front of our telescopes. The standard explanation points to the sun. As the object moves farther from our star, it receives less sunlight to reflect back toward Earth. That makes sense on paper. But here's where it gets strange. 3I/ATLAS passed its closest approach to the sun weeks ago. Most comets show a gradual, predictable fade after that point. This one, it's dimming faster now than it did right after perihelion. The rate is accelerating, and that's what has researchers opening their data files at 2 a.m. trying to figure out what they're missing. Despite this dramatic fade, 3I/ATLAS still ranks fourth among nearly 100 comets currently under observation. This isn't some dim, barely visible speck. This is a bright, active object that's doing something we can't fully explain. There's something else happening with this object that's been consistent since the day it was discovered on July 1st. Every 16.16 hours, the brightness pulses. Not approximately 16 hours. Not around 16 hours, give or take. Exactly 16.16 hours, measured across 5 solid months of observation. When scientists first noticed this rhythm, the explanation seemed obvious. The nucleus must be shaped like a potato tumbling through space. When the broadside faces Earth, we see more reflected light. When it rotates edge-on, less light reaches us. Simple geometry, nothing unusual. Then, Hubble Space Telescope looked at it on July 21st, and that simple explanation fell apart completely. What Hubble revealed changes everything. The light we're seeing doesn't come primarily from the solid nucleus at all. Most of it comes from a massive glowing halo surrounding the object, what astronomers call the Coma. You can actually see the tiny nucleus through this transparent cloud, but here's the problem. Based on Hubble's measurements, that solid core contributes less than 1% of the total brightness. Now we hit a wall of basic mathematics. If the nucleus only produces 1% of the light, how can its rotation create brightness changes of 30 to 40%? It can't. The numbers physically don't work. Based on Hubble's data, the nucleus is roughly 2.8 kilometers in radius. At that size, even if it were made of pure mirror, it couldn't cause the brightness swings we're measuring. This means the 16.16-hour periodicity isn't about a spinning rock at all. Something else is creating this rhythm, something happening on a much larger scale in the surrounding cloud of gas and dust. And that something has maintained clockwork precision for 5 straight months without drifting even 0.01 hours. Natural rotation periods vary due to uneven mass, jet-induced torques, and structural changes. Maintaining this precision requires either exceptional stability or something actively regulating it. Multiple teams have now documented structured jets shooting out from 3 I/ATLAS. These aren't the random puffs of gas you'd expect from ice getting heated by the sun. They're organized, directional, and they pulse in sync with that 16.16-hour beat. In late November, observers in Thailand, using a relatively modest 26-centimeter telescope, captured something remarkable. 2 prominent jets, one of them pointing directly toward the sun. That's called an anti-tail, and it matters because normal comet tails point away from the sun. Solar radiation and solar wind push gas and dust particles outward. An anti-tail pointing sunward means you've got particles of very specific sizes following unusual orbital paths. It's rare enough that most astronomers might go their entire careers without seeing one this prominent. Observations from Hawaii confirmed similar structures, with jets emanating in multiple directions at once. Every imaging session shows the same thing: active, coordinated material being expelled into space. The natural explanation is straightforward. A large ice pocket on one side of the nucleus faces the sun during rotation. Solar heat vaporizes it, creating a jet. When it rotates away, activity decreases. The James Webb Space Telescope measured these jets moving at 440 meters per second. At that velocity, material ejected during one 16-hour rotation can travel about 25,600 kilometers, more than enough to affect the brightness of the entire Coma. It's reasonable. It fits known comet behavior. There's just one problem. Where's the evidence? If this natural process is happening, astronomers should be able to watch it unfold. A series of images taken over several days should show the Coma brightening and dimming right on schedule. The jets should pulse on and off with that 16.16-hour rhythm clearly visible in time-lapse. No such study exists in the published scientific literature. Nobody has presented the movie that would prove this is standard comet behavior, playing out exactly as expected. That absence is striking given how much attention this object is receiving. Between November 28th and 29th, observers reported something even more puzzling. The jet structures changed significantly within just 24 hours. Images from Hawaii showed what looked like a complete reconfiguration. The anti-tail intensified while other jets shifted direction. These changes didn't correlate with any obvious external trigger like changing solar angles. It looked more like internal processes we can't observe were driving the surface activity. Let's step back and look at what we're actually dealing with. This object came from interstellar space. Its trajectory proves it's moving too fast to be gravitationally bound to our sun. It originated somewhere beyond our solar system, traveled for potentially millions of years through the radiation-soaked, near-absolute zero void between stars, and arrived here capable of producing these bright, structured jets. That journey should have been devastating. Cosmic rays bombarding the surface, impacts from interstellar dust at collision velocities measured in kilometers per second, temperature fluctuations from near zero to several hundred degrees as it approached the sun. Natural comets from our own Oort cloud often fragment under these stresses. They crack, crumble, fall apart. 3I/ATLAS is holding together, not just surviving, but maintaining organized activity patterns that suggest remarkable structural integrity. The ice reserves that fuel these jets survived intact across interstellar distances. The nucleus hasn't shown any signs of breaking up despite the thermal and gravitational stresses of solar approach. This is only the third interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, that strange visitor that accelerated in ways gravity alone couldn't explain, then vanished before we could study it properly. We missed our chance, and the astronomical community has regretted it ever since. The second was Comet Borisov in 2019, which behaved more conventionally. 3I/ATLAS sits somewhere between them, showing comet-like features but with behaviors that keep pushing against what we consider normal. Here's what makes the current situation so frustrating. Both Hubble and James Webb Space Telescope could observe 3I/ATLAS right now without any risk of solar interference. The orbital geometry is perfect for the next 2 to 3 weeks. After mid-December, that window closes. Observations become increasingly difficult, and if the dimming continues, by January the object might be too faint for detailed analysis. NASA hasn't announced any observing plans. No confirmed schedule, no official statements, no comments. That silence is interesting because these are the world's premier space telescopes, capable of resolving details ground-based instruments simply cannot match. Webb's infrared vision could penetrate straight through the Coma to analyze jet composition. Hubble's resolution could track structural changes hour by hour, finally creating that time-lapse movie, showing whether these jets behave naturally or not. The scientific value would be extraordinary. The astronomy community is split between pushing for immediate observation and counseling patience. But there's universal agreement on one point. This opportunity to study an interstellar visitor up close with our best instruments shouldn't be squandered. While professional astronomers debate, something remarkable is happening on the ground. Amateur observers with backyard telescopes are documenting changes in real time that can't be ignored. Belgian astrophotographer Julien Duinter captured images on November 25th, showing an unusually loose, ragged tail structure. 2 days later, Teerasak Thoiwong in Thailand documented those twin jets with clarity that rivals professional observations using just a 26-centimeter telescope. What they're capturing provides something major observatories with competitive schedules cannot match: continuous monitoring showing an object that's constantly changing. The tail structure they're documenting tells its own story. Instead of smooth, continuous particle streams, the tail shows distinct clumps and gaps, suggesting material is being released in bursts rather than steady outflow. It's visual evidence of that 16.16-hour cycle actively shaping what we see. We are at a decision point. The observation window for detailed Hubble and Webb studies closes in mid-December. Every day without new data is information permanently lost. The object will remain visible from Earth for months after that, but it will be dimmer, requiring longer exposure times that limit what we can analyze. This isn't about jumping to exotic conclusions. This is about recognizing when observations don't match existing models and gathering better data while we still can. Whether the final explanation involves unusual comet physics, rare ice compositions, or something we haven't considered, we won't know unless we look with our best instruments while the opportunity exists. 3 interstellar objects in 8 years. Before 2017, we'd never detected even one. Each has shown distinctly different characteristics, raising fundamental questions about what's out there and what happens during those million-year journeys between star systems. What we decide right now determines whether we get answers or spend the next decade wondering what we could have learned. So here's what we know for certain. An interstellar visitor is dimming while approaching Earth, breaking basic physics. It's maintained a 16.16-hour rhythm for 5 straight months with mechanical precision. Jets are firing in coordinated patterns that challenge natural explanations, and we have less than 3 weeks before our best observation window closes forever. This isn't science fiction. This is happening right now, documented by multiple observatories worldwide. Whether this turns out to be exotic comet behavior we've never witnessed, or something that rewrites our understanding of interstellar objects, the answer depends entirely on whether NASA points Hubble and Webb at this target in the next 2 weeks. We missed our chance with Oumuamua. We can't afford to miss this one. Now I want to hear from you. What's your theory on that 16.16-hour pulse? Drop your thoughts in the comments below, because right now everyone's trying to solve the same puzzle, and your perspective matters. If this video opened your eyes to what's actually happening in our solar system right now, hit that like button, subscribe to Galactic Breaking News, and turn on notifications, because when new Hubble or Webb data drops, you'll want to know immediately. We're tracking this story in real time, and the next update could come any day. Check out our latest coverage on SpaceX, Starship, and space industry developments. The universe is revealing its mysteries faster than ever, and you don't want to miss what's coming next. The clock is ticking, the data window is closing, and 3I/ATLAS is still out there, pulsing its rhythm into the void, waiting for us to understand what it really is.